Hi class, today we're moving into a new chapter. It's chapter 11, which is called Systems of Linear Equations, and that's a topic that should also be review. You should have learned this in beginning algebra or algebra 1, and also in intermediate algebra, which is algebra 2. And you should find most of this section is review. We're going to solve a system of two linear equations by three different methods: by graphing, by using the substitution method, and by using the elimination method. And so the last objective is to use these systems to solve applied problems. Just to recall what a system of equations is, it is a system that is composed of two or more equations in two or more variables, and we're going to consider all of them simultaneously. A solution to a system of equations is any ordered pair that makes both equations true at the same time. Question number 1 says to solve the following system of equations graphically. So what we want to do is graph both of these lines and then see what point do they have in common. And in order to graph it, I would say go ahead and use your graphing calculator. But in order to do that, you want to make this as a function or start off as y equals so that you can put it into the equation editor in your graphing calculator. We're going to start with the first equation. We want to subtract 3x from both sides. And you end up with y is equal to negative 3x plus 5. We've isolated the y, so we're done with that first equation. Let's now work with the second one. Let's first subtract 2x from both sides. And then we will divide by the coefficient, so we're going to divide everything by negative 5. And so we're left with y is equal to positive 2/5 x minus 9/5. And that would be a pain in the butt to graph by hand, but we can go ahead and use our calculator to graph both of these. Now you want to take both of these equations and put them in your graphing calculator. I'm going to be putting them in Desmos. Now technically in Desmos I could have typed them in exactly as they appeared in your notes, but I went ahead and solved for y for each of them so that you could see what it looks like when you put it into your calculator. And then it graphs the first line as a line with a negative slope with a y-intercept of 5. And then the second line is a positive slope with a y-intercept of negative 9/5. And if I want to find the point they have in common, I'm just going to hover over that point, and I find out that the point is 2, negative 1. My x value of 2 and my y value of negative 1. So 2, negative 1 is the point that is a solution to both of these equations, and so that's the solution to the system of equations. To solve this on your TI graphing calculator, you would want to click on the y equals button that's on the top left. It's a gray button. And then you want to enter the equations. The first equation would be y1, the second equation would be y2. And after you're done entering the equations, click on calc. And calc is two buttons. You'd hit the second button and then the trace button. So the second is a blue button and the trace is one of the top menu buttons as well. And then choose option 5, which says intersect. You can either scroll down to it and hit enter, or you can just type the number 5. And then it will ask you a few questions. I'll say first curve, and you can move your cursor to pick which line you want it to pick. And then it'll hit enter, second curve, hit enter, guess, meaning just move your cursor close to where they intersect, hit enter, and then it will give you the x and the y values. It'll say x is equal to 2 and y is equal to negative 1. So that's how you know what your solution would be. Now we won't be spending a lot of time solving systems of equations graphically. We're actually going to be using the other two methods much more often. However, it's important to understand the concept of what a solution means, and the graphing those equations helps us to understand. If we have two lines and they never intersect, then they are inconsistent because they don't have any points in common, and so they have no solution. However, if they do intersect, then we know that they're consistent because they have at least one point in common, they have at least one solution. And if they are the same line, then they agree everywhere, they intersect everywhere, and they have an infinite number of solutions. And so we have these different ways to name the types of situations that we have. And as we go through the methods of solving, we might say, hey, we only have one solution. We found one point that makes both of these equations true. That's the most common, the one in the middle. But we can still also get inconsistent systems or consistent dependent systems, and our answers might look a little bit weird. And so if we can understand the idea behind the graphs, then we know what it means when we're solving for it algebraically. Time solving it using the substitution method. Like it says in your notes, we're going to start by isolating one variable in one of the equations and then substitute that into the other equation. This method works best when you have a variable that has a coefficient of 1 or -1, because then it makes it easy to isolate. Also, before I begin, I label my equations with A and B so that I know which equation I'm talking about as I move along through the method. This is not as important with a two variable, two equation example, but as we move towards multiple equations, maybe with 3 variables and 3 equations, or even more, this is a very important step to keep track of your work. So I labeled my first equation A, my second equation B. And now I want to isolate the y in equation A because that has a nice coefficient of 1. So I'm going to subtract 3x from both sides, and I'll get y is equal to -3x plus 5. Now that I've isolated this variable, I'm going to plug it into the other equation, meaning into equation B. I'm going to write equation B, but I'm going to put parentheses where the y variable is. So I wrote 2x minus 5 times parentheses is equal to 9. Inside that parentheses, I'm going to put the value of y. It's -3x plus 5. And then we'll distribute and solve. Make sure you distribute that negative. Now that I've solved for one of the values of the variable, I'm going to plug that back into either A or B, it doesn't matter which, and I'm going to solve for the other variable. Let's plug it into equation A. So I'm going to write 3x plus y is equal to 5. I'm going to replace the x with a parentheses. And then in that parentheses, I'm going to put the value of x, which is 2. So 3 times 2 is 6. And then subtracting 6 from both sides, I get y is equal to -1. Now that I solved for both x and y, I'm going to put it in coordinate form, and notice that we have the same solution as when we solved the system of equations graphically. And for our third question, we're going to solve the following systems of equations using elimination. We're going to use that method for this question because neither of these equations have variables that are easy to isolate, so we're not going to use the substitution method. And when we have this method, what we want to do is figure out if we want the x's or the y's to add to each other so that they end up being eliminated from the equations. That is, which one of those do we want to cancel out? For this one, I think I want to eliminate the y's, so I'm going to write that goal down. Once again, also labeling my equations as A and B so I know what I'm going to do with them. The reason I chose to eliminate my y's is because they already have opposite signs. One of them is positive and one of them is negative. So that's going to make it easy when I add them together to eliminate them. But I want them to have the same coefficient, and so I'm trying to find the LCM of 3 and -2, and I'm going to make them into 6. So I need to multiply the first equation by 2 to make that a 6, and I'm going to multiply the second equation by a 3 to make a -6. Notice that I'm putting my instructions into my labels on the left-hand side. I'm going to multiply the equation A by 2. So that means I'm going to get 8x plus 6y is equal to 14, multiplying all the terms. And then my second equation, I'm going to multiply all of those terms by 3. So I'm going to get 15x minus 6y is equal to -60. And then you're going to add these equations together. I'm going to get 23x is equal to -46. Notice that the y's will cancel out when you add them together. Dividing both sides by 23, I get x is equal to -2. Now we have a choice. We could now do the same steps, but to eliminate the x's, and that way we could solve for the value of y, or I could take this value and substitute it into either of the equations to solve for y. Let's go ahead and use substitution at this time. I'm choosing to substitute into equation A, so I'm going to write 4 times parentheses for my x plus 3y is equal to 7. Substituting the value of negative 2 in wherever I see an x. That gives me negative 8 plus 3y is equal to 7. Adding 8 to both sides, I get 3y is equal to 15, so y is equal to 5. Now I have the value of x and the value of y, but you have to be careful. That's not two solutions. That is one solution that has both an x and a y variable solved for. And so the solution is one ordered pair, negative 2, 5. Our next question says we can use any method to solve the system of equations. So I think I'm going to do elimination again. Let's eliminate my y variables. It's easy to make that second equation match the first one in the y's. So I'm going to multiply my second equation by negative 2 so that they have opposite signs. We're not going to change the first equation, but I am going to multiply the second equation by negative 2, so I'm going to get negative 4x plus 2y is equal to positive 4. And when I add them together, the 4x and the negative 4x will cancel out, and so will the negative 2y and the positive 2y. We set out just to eliminate the y's, but we ended up eliminating both variables. And so now I have nothing left on the left-hand side. So now I just have 0 is equal to 9. And no variables, nothing that can happen to make this true. 0 is not equal to 9, and I can't, like I said, there's no variables left. I can't plug anything else in. So since this is not true, this is one of those ones that does not have a solution. So no solution. One of the ways that we write no solution in this class, it looks like a 0 with a line through it. Now I know some of you are using this as a 0. And you can't, because this is a symbol in math that means no solution. 0 is a 0 without a line through it. And this would be our system of equations that is inconsistent. Inconsistent because it does not have a solution. Number 5 also tells us that we can solve the system of equations using any method. But looking at the equations that we have, we notice that one of them is already solved for y. The y is isolated. So this sort of lends itself to using the substitution method. Let's go ahead and label our equations first. And so now we're going to substitute the values in b into equation A. Notice how I annotate my work in orange. We're now going to write equation A, replacing the y with a set of parentheses. So we get 3x plus 6 parentheses is equal to y. Inside my parentheses, I'm going to put negative 1/2 x plus 3/2. And you have to take good care to distribute that 6 properly. And we're going to get 3x minus 3x plus 9 is equal to 9. And when I simplify this, the 3x will add with a negative 3x to cancel out. And I'm going to be left with 9 is equal to 9. And notice that I already substituted my y out and then my x is canceled out. I'm left again with no variables. However, at this time, when there's no variables left, this equation is true. 9 is equal to 9. That means that these equations are equal to each other all the time. No matter the value of the variables, these equations are the same. So this is one of those situations where I have an infinite number of solutions. We would say that the system of equations is consistent because there's at least one solution, and it's dependent because it has an infinite number of solutions. Now, you may not use the terminology, this has all solutions. It doesn't, all the numbers you can plug in are not solutions. However, there's an infinite amount of solutions that you can find. Question number 6 asks us a mixture problem, and it says, a confectioner combines two types of candies into a mixture that costs $5.50 per pound. If the first candy costs $4 per pound and the second candy costs $7.25 per pound, find how much of each candy is in the mixture if the total mixture weighs 30 pounds. So there's some clue words that I want you to get used to doing in here. And one of the first things we want to do is read the question again. It says, find how much of each candy is in the mixture. So that informs of how I will choose my variables. I'm going to find how much of each candy. Now, it just says the first candy and the second candy. So I'm going to say how much of the first candy and how much of the second candy. It's important that you know if you're looking for the cost or if you're looking for the quantity. And so that word how much, or that phrase how much, tells us exactly that we're looking for how much does it weigh or how many pounds. Let's go ahead and set our chart up. Setting up our chart like this, let's go ahead and put our variables x and y in. Our number of pounds is x for the first and y for the second. Now let's go read the problem again. It says a confectioner combines two types of candies into a mixture that costs $5.50 per pound. That's for the whole mixture. If the first candy costs $4 per pound, and the second candy cost $7.25 per pound, and the total mixture cost $5.50 per pound, we can put all those values directly into our chart. There's one more sentence in here that we have not put into the chart, as the last part of the last sentence says the total mixture weighs 30 pounds. So if the total mixture weighs 30 pounds, means that the total pounds is going to be 30 pounds. So far we have in dark blue the price per pound, which was given to us in the question itself. And then we have the number of pounds, which we decided on the variables x and y. And that's sort of what we figured we are looking for. And then we have the 30, which is from the word problem itself. Now, we don't know the cost of each of these, but we can use the method to figure it out. The price per pound times the number of pounds is the total cost for each candy. So we're going to multiply those. So we're going to multiply these two columns to turn up the third column. So I'm going to get 4x, 725y, and 165. We're actually going to get our equations by adding up the number of pounds. So we're going to get an equation that says x plus y is equal to 30. And then we're going to add up the cost. And we're going to get 4x plus 725y is equal to 165. Now you can solve this using any method you want. But the important part is coming up to the correct system of equations and setting it up. So you might want to rewind and watch this again so that you understand how we fill this in. The dark blue is what was given to us. The light blue is what we were looking for. The green is also something that was given to us in one of the sentences. We multiplied the columns to make that third column, and then we're adding our pounds and our cost together. I'm going to multiply that first equation by -4 to eliminate my x's. Adding them together, I get $3.25 times y and 45. Using my calculator, I got y is equal to 13.846. Substituting that back into my first equation, I get x plus 13.846 is equal to 30. And solving with a calculator, we get x is 16.154. What does that mean? Let's go look at what our x and y variables stand for. They say how much of each candy. And so we look at the units and it says per pound. So we know that the units is pounds. So I'm going to translate this into the correct answer. We'll say 16.154 pounds of the first candy and 13.846 pounds of the second candy. Always make sure to refer back to your original question to make sure you're answering it. It says, find how much of each candy is in the mixture. We found how much of both the first and the second candy, and we've answered it using the correct units. You really want to take time to stop this, redo this question, and do the question that's in the book so that you can get practice at this method. Pause the video now so that you can do it. For this last question, it's asking us to find the equilibrium point. Recall that the equilibrium point is when my demand and my supply functions are equal to each other. Doing something like this is actually a method of substitution. I have my y equals 15 minus 1.25x, and I have my y is equal to 3 plus 0.75x as my two functions, and then if I say my y's are already isolated and I substitute one into the other, then I have both functions set equal to each other. This is a method of substitution. Let's go ahead and solve for x. I get 15 is equal to 3 plus 2x. Subtracting 3 from both sides gives me 12 is equal to 2x. And then dividing by 2 gives me x is equal to 6. Taking that 6 and plugging it into either function, I can say d of 6 is 15 minus 1.25 times 6. So I get 15 minus 750, which is just 750. So my equilibrium point is 6, 750. Notice that if instead we plugged 6 into my supply function, I would have gotten 3 plus 0.75 times 6, and that also would have been 750. And that makes sense. We should have gotten the same answer because this is the point that is a solution to both the demand and the supply functions. That's it for this section. Thank you. Go practice. Make sure you watch the video and that you practice the word problems especially. Have a good day.